Welcome, agents. Today, we're treating this not just as a standard study session, but as a high-stakes tactical mission briefing. Your primary objective? Absolute mastery of the fetch-execute cycle and register transfer notation for your Cambridge Computer Science exams. Whether you're operating under syllabus codes 0417, 0478, 0983, 0984, 2210, or our primary target today, the Advanced 9618, the mission remains the same. Extract maximum marks from a hostile exam paper in under 20 minutes. Look, I see two types of candidates go into the exam hall. We've got Alex. Alex overloads on raw computer science facts, memorizing every textbook definition, but provides zero analytical depth. Then we have Sam. Sam rushes the paper, completely misses the command word requirements, and ends up answering a question the examiner never actually asked. Both of them leave easy marks behind. If you want to extract those marks, you need a highly structured, strategic approach that actively demonstrates how a CPU processes data at the microscopic level. You're going to learn exactly how to analyze computer architecture, write perfectly formatted notation, and execute your answers like a top-tier candidate. Grab your tactical notebooks, because we are about to deconstruct the absolute core of CPU operations.
Okay, let's dive into this. 15%. That is not just a random statistic. The fetch-execute cycle and register transfer notation combined account for approximately 15% of the total marks in Paper 2 of your computer science exam. Just think about that for a second. That is a massive chunk of your final grade sitting in just one single topic area. It is the difference between an A and a C. You simply cannot afford to leave these marks on the table by giving vague, waffling answers about how registers communicate. The exam board wants precision. They want to see the exact flow of data across the address, data, and control buses. When you understand the sheer weight of this topic, you realize that mastering it isn't just a good idea. It's absolutely mission-critical for your success.
Here is our mission dossier for today's briefing. We will move systematically through 5 phases. Section 1, the 15% target. Section 2, architectural core principles. Section 3, the technical methodology. Section 4, critical analysis. And finally, Section 5, examiner minefields.
Let's initiate Phase 1. The 15% target.
A lot of candidates, like our operative Alex, walk into the exam hall relying purely on superficial breadth. They try to memorize raw, isolated terms like fetch or decode and just dump them onto the page hoping something sticks. But relying on raw memorization is a completely losing strategy. The academic benchmarks for this topic explicitly require logical, structured reasoning. The winning strategy? Analytical depth. Examiners aren't just looking for you to repeat that a fetch happens. They want to see your logical progression. This is where we introduce the PEAL framework: point, evidence, explanation, link. For example, your point might be that the memory address register receives data. Your evidence is the specific register transfer notation. Your explanation is detailing why the MAR needs the address from the program counter before any data can actually be retrieved from memory via the address bus. And your link ties it back to the specific scenario in the question. That is how you secure the bag.
Moving on to Phase 2, architectural core principles.
To defeat the exam, you need to understand how the enemy, the examiner, thinks. The assessment objectives are split into 3 distinct cognitive domains, and you need to decode the command words to know which one you are in. First, knowledge and understanding. This is triggered by command words like state or identify. It's knowing the basic facts, like identifying that the accumulator holds the results of ALU operations. Second, application. Command words like trace or demonstrate. This means using your knowledge in a specific scenario, such as tracing register transfer notation for a brand new assembly instruction. And third, analysis, triggered by words like explain, compare, or evaluate. This requires breaking down complex systems to explain how data buses and control buses interact during the cycle. Before we continue, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay. So when you evaluate a question, you must match your answer format perfectly to the cognitive domain the examiner is targeting. Sam always misses this, writing a knowledge answer for an analysis question. Don't be like Sam. Now, listen closely, because here is a massive secret to unlocking top grades straight from the Cambridge Principal Examiner reports. The examiners explicitly state that candidates referencing cross-topic connections achieve significantly higher marks. You cannot treat the fetch-execute cycle in a vacuum. It doesn't exist in isolation. When you demonstrate how the cycle connects to memory management, to general CPU architecture, or to specific assembly language programming execution, you instantly signal to the examiner that you have a comprehensive mastery of the subject. You aren't just reciting a textbook. You actually understand how a computer works. Think about how an interrupt alters the normal cycle. The contents of the program counter and current registers have to be pushed to a stack in memory. Mentioning that interplay is exactly what pushes a standard answer into the top-tier grade boundary.
Initiating Phase 3, the technical methodology. Time to get our hands dirty.
Top candidates follow a strict algorithmic framework to build their answers. Think of it as your computer science success blueprint. First up, step-by-step decomposition. In the context of the fetch cycle, that means breaking the sequence down flawlessly. Step 1, the contents of the program counter are transferred to the memory address register. Step 2, the program counter is incremented by 1, so it points to the next instruction. Step 3, the address in the MAR is sent along the address bus to main memory, and a read signal is sent down the control bus. The data at that address travels back along the data bus to the memory data register. Step 4, the instruction in the MDR is copied into the current instruction register. Second in our framework, you select the right data representations. Third, you implement precise code, in this case, exact register transfer notation. And finally, rigorous testing, mentally verifying that your logical sequence actually flows correctly without skipping any vital bus transfers.
Once you have your foundational framework, you execute a standardized, systematic sequence for every single question you face. Imagine you're staring at a blank page. Step 1. Identify the key architectural elements requested by the command word. Does it ask about the decode phase or the execute phase? Step 2. Apply the relevant core principles. In computer science, applying principles means utilizing precise RTN syntax. You need to know exactly when to use square brackets to denote the contents of a memory address and when to use the directional arrow to denote data transfer. Step 3. Execute your analysis with absolute clarity, applying that peel structure we talked about: point, evidence, explanation, link. And step 4. Verify your results. Does your final answer clearly map to the scenario provided in the question prompt?
So the crucial point I need to hammer home here is the method mark strategy. In Cambridge exams, marks are heavily awarded for the process. If you show logical, step-by-step structured reasoning for how data moves through the CPU, you pick up method marks along the way. Let's say you're writing out a complex RTN trace for an execute phase, and you make a tiny error at the very end. If your analytical working is clear, step-by-step, and logically sound up to that point, that working acts as a safety net. It captures valuable method points. Always document your process. Never just write the final step and expect full credit.
Phase 4. Master the critical analysis. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exams strategy sessions. All right, let's get back to the mission. We are now entering an interactive workshop phase. To conquer those brutal higher-order 8 to 12 mark questions, you must employ evaluative thinking. I want you to use the specific checklist for extended responses. First, consider multiple solutions or architectural approaches. Second, analyze the trade-offs. For example, if a question asks about increasing the width of the data bus versus increasing clock speed, what are the pros and cons? A wider bus moves more data per cycle, but might be more expensive or complex to manufacture. Third, acknowledge the limitations of the system you are discussing. And most importantly, justify every single technical decision with concrete evidence. If you claim an instruction cycle takes a specific number of clock ticks, back it up with the exact RTN steps that prove it. Let's run a rapid-fire speed writing challenge. When handling questions that ask you to compare approaches, say comparing direct addressing to immediate addressing during the execute phase, comparative analysis requires strict rules. You have 30 seconds in the exam to plan this out. Rule 1. You must identify both similarities and differences. Rule 2. Don't just list facts side by side like Alex does. You must use comparative connectives, where it's like whereas, conversely, or in contrast. Rule 3. Support each comparison with technical evidence. Immediate addressing loads the operand directly, whereas direct addressing requires an additional memory fetch. And Rule 4. Draw relative conclusions about their efficiency. Immediate is faster, but limits the size of the data you can use. Boom, perfect PO paragraph executed. Initiating our final phase, Phase 5, navigating examiner minefields. Look at this red alert straight from the Cambridge examiners. Quote, candidates consistently confuse key terminology. This is where Operative Sam usually fails. It is a catastrophic, yet entirely avoidable mistake. The rule here is absolutely non-negotiable. You must always define your terms before you use them in an extended response. If you are writing about the accumulator, the program counter, or the memory data register, do not assume the examiner knows what you mean, and do not assume they will give you the benefit of the doubt. Define its role briefly before diving into your complex register transfer notation analysis. It anchors your answer, proves your baseline knowledge, and sets you up for maximum mark extraction.
Let's sweep for the top 3 specific minefields so you can avoid blowing your grade. Minefield number 1, forgetting edge cases. The most classic dropped mark in computer science history is failing to show the incrementation of the program counter right after the MAR is loaded before fetching the next instruction. If you don't increment the PC, you are stuck in an infinite loop fetching the same instruction. Minefield number 2, completely missing boundary conditions in your logical reasoning, like what happens if an arithmetic operation causes an overflow in the accumulator. And minefield number 3, providing generic, memorized textbook answers that are not specific to the context given in the question prompt. If the exam specifies a CPU with a 16-bit address bus and an 8-bit data bus, your trace and your explanations must perfectly map to that specific given architecture.
To bypass that first trap of confusing terminology and dropping steps, here is an incredibly actionable memory hack. Create a mnemonic for the sequential stages of the fetch cycle using the first letters of the key terms. For example, please make it my computer. P for program counter, M for MAR, I for increment PC, M for memory to MDR, and C for CIR. Please make it my computer. Having a simple, highly personalized mnemonic tool gives you instant, reliable access to the correct sequence under massive exam pressure, ensuring you don't drop a vital stage of the CPU cycle when the clock is ticking down.
Let's pull this entire mission together into your ultimate cheat sheet recap, the extraction strategy. When you open that past paper, apply our 3 rules that guarantee top marks: command word decoding, the Peel framework, and a time management matrix. Run these 5 steps. 1. Deconstruct the question based on the targeted cognitive domain. 2. Extract the relevant CPU data and context. 3. Select your analytical framework. 4. Execute your step-by-step register transfer notation cleanly, obsessively checking your square brackets. And 5. Present your final answer using precise, predefined terminology. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. We've outlined the 15% target, the core architectural principles, the methodology, the analysis, and swept the minefields. Your mark potential just went from 0 to 100%. The intelligence is now securely in your hands. But remember, strategy without execution is just theory. So, I leave you with this final, critical challenge. How will you actively apply this step-by-step framework to completely deconstruct the very next fetch, execute, practice question you attempt? Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with your study partner. Extract those marks systematically, master the cycle, and remember, ace the exams. Your Cambridge success starts here. Good luck on your mission.